Okay, in question 38 on the review packet, they're asking us if you are trying to operate where marginal revenue equals marginal cost, what production level is indicated. So you're going to try to find the x. So first you need to establish marginal revenue. So marginal revenue is just the first derivative. So that's going to be 100 minus 0.02x. Okay, so that's important. Then you're going to need to get marginal cost. So costs equal 50x plus 10,000. So therefore marginal cost is going to be just 50. Okay, so you're going to set marginal revenue equal to marginal cost because that is what they're asking us to do right there. So 100. So what I'm doing, let's just make this clear. This is what I want to do. So now let's do it. 100 minus 0.02x equals 50. Okay, so I'm going to say 100 minus 50 equals 0.02x, and then 50 equals 0.02x. So then what we're going to do is just divide 0.02x by 0.02, divide 50 by 0.02, and you should be getting that your x, where you want to operate, is going to be 2500, and we'll call it units. Okay, so that's question 38. We're going to continue with question 39 on the next slide. Okay, so to do problem 39, it's all about finding the minimum cost. So you're going to take the first derivative, like I've done right here, and you're going to then set it equal to 0. Okay, so the first derivative becomes 3x squared minus 10x minus 13. Okay, you're going to have to factor that. That's a hard factoring. I set up how I did decomposition over here. And my factors end up being x plus 1 and 3x minus 13. So look over that procedure if you need to refresh on this. That leaves me with the critical values of -1 and 13 over 3, and I got those by setting my first derivatives equal to 0. So now I'm going to have to figure out if I found the minimum, if they're one of these two, by doing first the first derivative test. So here is my first derivative test, and when you do a first derivative test, you are testing on either side of those critical values. So here's my sign chart, -1, and this is 13/3. So I'm going to focus my attention right over here on these factors. And if I pick a number to the left of -1, let's say I pick -2, and if I plug in -2 here, I get a negative, and here I'm going to get another negative. A negative times a negative is a positive, so I put a positive there. Now let's test a number between the two critical values, and let's say that I'm going to test a 0. You don't need to write these numbers down, but I sometimes find it easier to do so. If I plug a 0 in my first factor, I'm going to get a positive. Oops, excuse me. That's going to be a positive. If I plug a 0 in my second factor, I'm going to get a negative. A negative times a positive is a negative. Okay, so the decimal equivalent of 13/3 is 4.3. So why don't we test 5? Let me erase these evaluations and say if I plug a 5 into the first factor, that's going to be positive, and that's also going to be positive. A positive times a positive is a positive. That's my sign chart. The analysis gives me positive slope here, negative slope here, positive slope here. So I'm going to also write that I'm testing f prime of x. And we know with every first derivative test, you have to give me a statement as well as a sign chart. So I would say for my statement, so let's see what I want to do that. So I'm just going to say at the critical value of -1, the slope changes from positive to negative, and therefore that gives me a max. Remember, you always want to have a conclusion. Okay, then the next part of this is going to say at the critical value of 13/3, the slope changes from negative to positive, and therefore I have a min. So right now I am finding that a minimum quantity of 13/3 or 4.3 provides my minimum cost. Okay, so that's the first derivative test. So let's go on to the next page and we will do the second derivative test. Okay, so on this page what I've done is I've gone back to the original function and I have taken the second derivative. So that's the second derivative here. Now, the second derivative test does not mean that you're testing an inflection point that I would have gotten by taking the second derivative and setting it equal to 0. That's not my purpose. My purpose is to use the second derivative to test the critical values we attained by setting the first derivative equal to 0. So just to refresh, those two critical values were -1 and 13/3. When I did a first derivative test, which I did back here, I tested on either side of the critical values rather. Now doing a second derivative test, I don't do that. I instead test right on top of these critical values. Take your -1 and plug it into your first derivative. Your second derivative. When I do that, I get a -6 minus 10, which is negative. If I have a negative, that means my function is concave down. And what is negative? What was negative was the second derivative evaluated at the critical value of -1. That's what was negative. That gives me a concave down, which is actually a max, and that affirms what I found with the first derivative test. Now let's move on to the second critical value of 13/3. If I plug in a 13/3 into the second derivative, I'm going to get a positive. What did I get that was positive? The second derivative evaluated at 13/3 was positive. This gives me a function, or this tells me the function's concave up, which affirms the fact that I had a minimum at 13/3. So with every test you have to have a statement. And the statement is, so I would say f prime prime, notice the wording is a little different from the first derivative test, of -1 that is less than 0. Therefore, the function is concave down, which yields a max. Okay, so in the second derivative test, you have to tell me what happened, and you have to tell me the result on the concavity, not on a slope. And you have to give me a resultant statement. Therefore, I have a max. Okay, the second statement is going to be f prime prime of 13/3 is greater than 0. So therefore, my function is concave up, and that yields a minimum. Okay, so I am finding that if I wanted to figure out the minimum cost, I would evaluate the cost function at 13/3. So let's go back and we're going to get the cost function. Okay, so the cost function was right here. All right, so let me type that over here on the next page. Oops, excuse me. And then this is what we're going to do for our final statement. So I'm going to say, plug in my cost function. So I really want C of 13 over 3. And that's going to be 13 over 3 to the third minus 5 times 13 over 3 squared, and then minus 13 times 13 over 3, and then plus 150. All right, so my final answer is, if I want to minimize cost, I want to produce 13 over 3 units, and my minimum cost, my minimized, I should say, cost, will be $81.15. Okay, so that's the final answer. This is an important question because I go through the first and second derivative tests. I explain that I did not test the inflection point at any point, and my conclusion is that I have a minimum cost of $81.15 when I produce 13 over 3 units, which is about 4.3 units. So in reality, I'd probably be producing 4 units to minimize my cost, since I can't really produce 4.3 units. So if I do a reality statement, let me just see what I get for my cost. Your value of your X is 4. So that would be a minimum cost of $82. Okay, so that's how I would do it. Because what if I produce 5? Let's see what I would have. Yes, so definitely in terms of giving this problem a practical sense, you would say that you would produce 4.3 or 4 units to minimize your cost. Okay, and that's the end of the review packet.